started looking into the applications of the electromagnetics. So we concluded our oblique incidence, and then our first application was transmission lines. And these are the examples of the transmission lines. And all these transmission lines, they support the simplest, which is the transverse electromagnetic wave, which is the TEM wave. And I gave a very nice example of the coaxial transmission line, how the electric and the magnetic field can carry the electromagnetic energy. However, as I discussed that for the transmission line, especially for a very simple type of transmission lines, we do not require to go into the electromagnetic theory. And therefore, we tried to use our circuit theory with some, modifications. And the modifications were, we did not use the lumped element circuits. We used the distributed element circuits, because this is what prevails when the interconnections between the circuits is greater than the 0.1 lambda, and which is typically the case for the transmission lines. And then we started with a small piece of transmission line of very small elemental length delta Z, and our objective was to find these voltages and currents, how they behave here. That means we need to solve them. And then we took a model, which is called as the L model, where we got the resistance and inductance and the conductance and the capacitance. And again, remember, this resistance is coming from the conductor. It is from the conductor. So it is coming from the conductivity of the conductor. And this conductance is coming from the conductivity of the dielectric, which is separating the two mediums. And this is your inductor, and this is your capacitor. This is because of the capacitance effect between the conductors. And we know that the inductor, if any metallic conductors, if it carries current, then you will see the inductance because of the two conductors. So this is put like inductance. Okay, and then we solved it. We used the Kirchhoff's voltage law and Kirchhoff's current law. We solved it, and eventually we got what is called as the telegrapher's equation in time domain. And in order to further solve it, we used the phasor analysis, and in the phasor analysis, we got this as our telegrapher's equations. And then after solving it, this is the summary. I will show it here. This is our summary. So our summary is that after solving, we got our voltage waves solution as V0 plus e power minus gamma z for positive traveling waves, and the current wave as I0 plus e power minus gamma z, where V0 plus and I0 plus are the amplitudes of the voltages and the current respectively. And we have seen in the time domain that it is actually a traveling sinusoidal wave. Alpha is the attenuation constant, beta is the phase constant, where gamma is the propagation constant, which is alpha plus j beta. Then we got our impedances as well. The characteristic impedance is the ratio of the forward traveling wave voltage amplitude over the current amplitude, which is root of z over y, and propagation constant is root of z times y. So this is for the positive direction. Similarly, we also got for the negative direction, those voltage and current waves which are moving in the negative direction. So after this summary, we can see that all these solutions that we got, it was very simplified. It was just 1D traveling wave equations, and the expressions that we got for our voltage and the current waves and the characteristic impedance and the gamma, our propagation constant, which is alpha plus j beta. This is very, very similar to the transverse electromagnetic wave that we have studied in our previous chapter. Okay, but here we used the circuit theory to make things much simple for us. Now let's continue. So this was the summary. So now what we are doing today. So today we are going to now look at a couple of examples and some special cases of transmission lines. So it is saying that we have a transmission line, and the transmission line has the following parameters: the resistance, the inductance, the conductance, and the capacitance. And guys, usually these values will be given by the manufacturer's data. Okay, and the line is operating at 8 megahertz, and we need to calculate the characteristic impedance, attenuation constant, phase velocity. And we need to answer whether my transmission line is lossy or lossless. So what is your Z naught? We know it. It is root of R plus J omega L over G plus J omega C, which is root of Z over Y. So we know all these R, L, G, C values, we will substitute. Okay. And remember, here all your resistance, inductance, conductance, capacitance, they are of per length. They are normalized to the length, which we discussed in the last class, because all these are distributed along the complete length. So in order to quantify it, we use per length. We normalize it to the length of our transmission. So once you substitute here, so here you need your calculators, and then you will see that this is my impedance, which is around 40 ohms, angle minus 36 degrees. Okay. Now, next is alpha and beta. How do you find alpha and beta? So you can find alpha and beta by first finding the propagation constant. And I know that my propagation constant is root of R plus J omega L times G plus J omega C. So again, if you substitute and do the simplifications, then I will get gamma as 1.30 angle 53.5 degrees, or in terms of the real and the complex part, this is my gamma. And if I compare this with my expression of gamma, which is alpha plus J beta, I can say that my alpha is 0.7749 neperts per meter, or as I told you, people also use per meter, a meter per minus 1. And this is my beta, which is 1.0501 radians per meter. This is my beta. Okay, and the phase velocity U is omega over beta. So you just substitute, you will get this. And last thing, whether the line is lossy or lossless. What can you say whether the line is lossy or lossless? See, you are getting alpha. Can you see this? So your alpha is non-zero. Alpha is not equal to 0. So if alpha is not equal to 0, that means the line is lossy, right? Because we know the definition of lossless. Lossless line or lossless case is the case when my attenuation constant is 0. But here my attenuation constant is not 0. That's why obviously it's a loss. Okay. So this was a simple example of how we can find different parameters of a transmission. Okay. So now we will go and look at two special cases of our transmission line. So these are the two special cases, and these are called as lossless transmission line and distortionless transmission. So what is a lossless transmission line? So these are the special cases. So lossless transmission line is the line where the conductivity of my conductor, that means, the conductor, the metal, the conductors that we took, to make the two, say, conducting paths for positive and negative, that is infinite. And then the conductivity of the dielectric, which is nothing but the this is the conductivity of dielectric is C. Okay, so this is for the conductor of our transmission line, and this is for the dielectric medium, which is separating the two conductors. That means the R is 0 and G is C. Then it is called as a lossless transmission line. In this case, so if you want, we can also go to the textbook and see. So this is our textbook, and this is the condition for the transmission. Okay. Now, if we have this as the transmission, this is the lossless transmission line. Let's now simplify our expressions. So in this case, what will be my characteristic impedance Z0? R and G, if they become 0, then it is simply becomes root of L over C. And my gamma, which is R plus J omega L and G plus J omega C, it will become simply J omega root of LC. In that case, my gamma, which is alpha plus J beta, see here, my gamma, which is alpha plus J beta, if I equate with J omega root of LC, what I'm seeing? I'm seeing my alpha is 0 and my beta is omega root of LC. So my attenuation constant is now becoming Z. That's why it's a lossless transmission. And in this case, your U is omega over beta. So which I can now simplify because I know my beta is omega root of LC. So omega over omega root of LC is nothing but 1 over root of LC. And if we compare these expressions with our lossless TEM transmission, then if you see here, my characteristic impedance is becoming root of LC, which is very similar to eta, which is root of mu over epsilon. Then my phase velocity, which is becoming U as 1 over root of LC, is very similar to the TEM wave in the lossless case as 1 over root of mu epsilon. Okay, so this is the simplified expressions for the lossless case. Now, let's take one example. So the example is saying that in our previous example, assume that the transmission line is lossless. So we need to go and we need to find all these parameters again. But in this case, assume that my line is lossless. That means my R is 0 and my G is 0. So if R and G both becomes 0, then what will happen to these characteristic parameters? So now, if we do it, my Z0, we will use the simplified expressions. It is root of L over C, which is 21.4 ohms. My attenuation constant is obviously 0 because it's a lossless case. And my phase velocity is 1 over root of LC, which is this value. And then my beta is omega over U, which I can get it in this way. Or if you want, you can get beta using this expression. It's up to you. Then the second special case. Okay, so what is the second special case? The second special case is called as the distortionless transmission line. Okay, so what do you mean by distortionless transmission line? Transmission line is called as a distortionless transmission line when R over L ratio is equal to G over C ratio. Or it is called as a distortionless transmission line when my attenuation constant alpha becomes independent of omega. So that all the frequency components which is in the signal, for example, your voice signal or any signal that is being transmitted, all the frequencies should be attenuated with the same value. And the second condition is your beta, which is the phase constant, is linearly dependent on the frequency. That is, beta should be proportional to omega and alpha should be independent of omega. These are the conditions that is satisfied by the distortionless transmission line. And in order to satisfy this condition, now when we come to the characteristics of our transmission line, then when we make sure that this ratio is equal to this ratio, then this is satisfied. And these, making sure that these ratios are maintained is in our hands, because this is purely coming from the characteristics of the transmission line, that is coming from the conductors that you are using and coming from the dielectric material that you are using in the transmission line. So you pick up the materials of the conducting material and the dielectric material in such a way that this is satisfied. Then you can make the distortionless transmission. And let's see, when this is satisfied, are we really making sure that this is happening? We can check here. So if you see here, so first what we are doing, first we are finding now what is the characteristic impedance in this condition. So my characteristic impedance Z0 is root of R plus j omega L over G plus j omega C. Now, since these two ratios are equal, that's why I'm taking L common from the numerator and C common from the denominator. And then what I'm saying is if this and this are equal, then whatever is inside the bracket can cancel out and I will get as root of L over C. So this will be my characteristic impedance. And what will be my propagation constant? R plus j omega L, G plus j omega C. So we can do the same thing, do a little bit of simplification, and we will end up with this one. We will end up with R root of RG plus j omega root of LC. And now if I compare it with alpha plus j beta, what I'm seeing that alpha is root of RG and beta is omega root of LC. And now U will be 1 over root of LC. You can check. And therefore, now looking at the expressions of alpha, beta, and U, I can assure that my alpha no longer has any omega term here. So that means it is independent of omega. And beta is just a function of omega, as we have already seen for the TEM waves. Omega root of LC. But remember, your distortionless transmission lines is lossy. Now let's take an example. So the example says that you have a transmission line which is operating at 8 megahertz. And this is the resistance, inductance, conductance, and capacitance values. And now our question is the transmission line distortionless or not? Then we need to find the characteristic in check first. So R over L. So R over L and G over C, they are the same. And therefore it's distortion. And now you can go and use the expressions of the characteristic impedance, which is root of L over C, which is now 408 ohms. Alpha, root of Rg, which is 0.122 nepers per meter. And the phase velocity, which is this one. Okay. Beta is omega over U, which is 0.037 radians per meter. And what is your wavelength? We already got it in our TEM case. Your lambda or beta is 2 pi over lambda, or lambda is 2 pi over beta, which is 170 meters. Or you can also get lambda as U over F. Where what is U? U is your phase velocity. Okay. So this is an example, and there is one point you to go and look at this. So see here, our phase velocity is exceeding the velocity of light, which is coming as a surprise, right? See, this is greater than 3 times 10 to the power of 8. This is possible. The phase velocity can exceed the velocity of light. The group velocity, okay, group velocity, phase velocity and the group velocity, they are different. Velocity is the velocity by which our energy packets are moving. Okay, our energy packets are moving. That is called as the group velocity. And this group velocity, it cannot exceed C. But the phase velocity can exceed. So go and, dig a little bit more about this and you will understand. And I will also see, because of the time constraint, I might not be able to spend too much time on this, but I will also see if there is a good YouTube video on this. If I can find a good YouTube video explaining that, I will share it. Okay. So this actually concludes our transmission lines. So although you can see that the chapter is very huge, but we have a lot of sections deleted. So if you see here, it is almost the whole chapter is deleted except the few, the first few sections. So if you see here, so chapter 11, so 11.4 to 11.10, this is all removed. So that's why. So if you see here, 11.1, 11.2 is the transmission line parameters, which we did it. And 11. Where it is. 11.3 was the special cases. And from here, it is excluded from the material. Okay, so this actually concludes the transmission lines. And the main objective, again, I'm re-emphasizing to introduce this transmission line is just to give you guys a flavor of how, the EM applications in the transmission lines are. Although we did it with a voltage wave, with a circuit theory, but still you have seen that the expressions that we got for voltages and currents are very, very similar to what we have seen in our TEM. Okay, so this actually finishes our transmission lines. And now we will go to our next part, which is our chapter number 12, which is rectangular waveguides. And before that, let's have a couple of poll questions. So ready? I'm going to say share the poll questions, very simple poll questions. And you have 40 seconds. Okay, so here is the question. For a normal incidence of the TEM wave on a boundary or an incidence, okay, the angle of incidence with respect to the normal of the interface is. Ten more seconds. 4, 3, 2, 1, and that's it. So what is the answer of this one? Yes, Thabit, can you tell me what is the answer of this one?
90.
90, is it correct? 90. How about others?
0.
0. 0 is correct. Why it is 0? I discussed this, guys, in the, I think on Thursday's class. I explained this to you. If this is my interface, okay, this is my interface. And we always measure the angles with respect to normal to the interface. So this is my normal to the interface. And in the normal incidence, my light is shooting like this, right? In normal incidence. So what is the angle of incidence it is making with respect to the normal? They are parallel. So what is the angle of incidence?
0.
0.
0 degrees. Got it? 0 degrees. We discussed this in the class. Okay, so next question. So again, for 40 seconds, the angle at which there will be no transmitted field in the other region in an oblique incidence is called this is very easy. Four, 3, 2, 1. Guys, okay, so it's time now. Yeah, so this, I think all of the most of the students took it correctly. The angle is called? Yes, anybody can answer. It is called as a?
Critical angle.
Critical angle. It is called as a critical angle, where you will not have any transmitted field. Okay, so now let's go to our next chapter, which is our chapter number 13. Sorry, 12. So chapter number 12, again, here our objective is to give you guys some flavor of the application of electromagnetics. And again, here we will not be covering all the sections. You will see in the here that what sections are all removed, 12.5 to 12.10. So we will just take from 12.1 to 12.4. Okay, so let's start. So if you see here, now waveguides, we have already talked about waveguides. right? We already talked about them as a guiding medium. So you are trying to guide your electromagnetic wave so that it can travel only in a certain direction. So unlike in the previous case, in our transmission lines, as I told you, in the transmission lines, they can support the TEM wave. So those transmission lines, they can have the transverse electromagnetic wave. Okay, that is no component in the direct, no component of electric or magnetic field in the direction of propagation. But now, because you have, restricted some guiding medium, that means you are enforcing your electromagnetic wave to travel in a certain direction. So in such case, your electromagnetic wave will no longer be TEM. That means especially our rectangular waveguide, which I'm talking about now, it cannot satisfy the transverse electromagnetic wave. And this is purely coming from the boundary conditions. Okay. And also what will happen is, with this waveguide, because you are restricting it to only travel in a certain direction, not all the frequencies will be able to travel. There will only be certain frequencies that it can travel. So you can think that your waveguide is becoming a sort of high pass filter. Any frequencies below cannot travel. Any frequencies above it can travel. So these are all coming again from the boundary conditions and the conditions that is to be satisfied in order for the electromagnetic wave to travel in a certain direction. So now we will look at it. So these are some simple pictures of our rectangular waveguide. It is rectangular metallic waveguide. That means the boundary, see all the four sides, they are made up of metal. So this is cross section is rectangular, cross section is circular. This is an elbow, which is 90 degrees bending. This is twisting. These are all rectangular waveguide. And the electromagnetic wave travels in this rectangular waveguide. Now, may I know, where have you seen this rectangular waveguide? You have seen it in your lab. In which experiment? And where did you see this? Yes.
For the polarization.
Sorry? Yes, for the polarization, experiment number 8 and experiment number 9, both. Wherever you are using the horn antenna. So you used it in polarization to check the polarization in experiment number 8. So your horn antenna was connected to the rectangular waveguide. And since you are going to use horn antenna even in experiment number 9, so there also you use the rectangular waveguide. Okay, so now regarding the analysis, let's start our analysis. And this is our analysis. So this is my cross section of my rectangular waveguide. And the inside part, it can be air or it can be any dielectric material. But so here we are just saying that it has a dielectric constant epsilon, and the length is A and the height is B. And again, here we are now going and we are applying the boundary conditions. So if you see here, because you have metal here, metal here, metal here, metal here, what will happen? The wave will experience complete reflection from the metallic walls and cannot spread in the transverse direction. So if I want the electromagnetic wave to travel here, the electromagnetic wave cannot travel everywhere it likes. In example, in free space that we did it in our chapter number 10. So the electromagnetic wave was traveling, we took an example that it is traveling in the Z direction, but in general, it can travel anywhere in any direction. But here we are not stopping it to travel, to move in this direction and this direction. Okay, so in these direction, it will be restricted and it will be forced to travel either inside the screen or outside the screen which is maybe positive Z or negative Z direction, which is our propagation. And we are restricting here. And this restriction comes from the boundary conditions. So therefore, boundary conditions becomes very important for us in order to understand the metallic waveguide. So now what I'm going to do now is I'm going to first derive a very general boundary conditions. And this general boundary conditions we are going to use when we solve the wave equation for this rectangular wave. How we solve the wave equation for our unbounded medium? We will solve a similar wave equation, but here for the bounded medium. But first, we need to get the boundary conditions. So I'm just summarizing the boundary conditions, and I'm getting a very general boundary conditions. So if you see here, when I'm saying very general boundary conditions, I'm not restricting myself, or I'm not telling myself that this is my x-axis, this is my y-axis, this is my z-axis. I'm not saying anything. I'm just saying that this is the tangential. This is the tangential direction, and this is the normal direction. So I am getting the boundary conditions in terms of tangential and normal components. And here is my dielectric material. So this is my dielectric material, and this is my conductor. So that's why if you see here, for the conductor, I'm saying that there is no electric field and no magnetic field. So both are zero. So you will have the electric field and the magnetic field only in the dielectric region. And if you see here, I'm writing the electric field not in terms of x, y, z, in terms of tangential and normal component. So they see here, that's why I'm writing as ET, AT, and ENA. So this is the tangential component, this is the normal. And here also tangential component and the normal. And now if I apply the boundary conditions, so what is the boundary conditions that we have studied in electrostatics? The tangential components are equal for a charge-free region. So E1 tangential must be equal to the E2 tangential. But here, if you see here, there is no electric field here. So then this must be equal to 0. So therefore, E tangential is equal to 0. Very well known to us. Second, the normal component of the magnetic field. B1 normal must be equal to B2 normal. And now here, mu1 H1 normal is equal to mu2 H2 normal, where mu1 and mu2 is for this and this region. But we don't have the magnetic field here. In region 2, this is 0. So therefore, H normal should also be equal to 0. So therefore, we have two boundary conditions. We got two boundary conditions, which is E tangential is 0 and H normal is 0. And guys, I'm not using 1 and 2 here because this is for the conductor, and here I'm not giving 1 because we have only one electric field here and one magnetic field. That's why. But now these are the two boundary conditions. So, however, for our rectangular waveguides, these two boundary conditions are not enough for us. We will require two more boundary conditions. Why? Because we will have 4 unknowns. You will see it later. So in order to get 4 unknowns, I need to have at least 4 boundary conditions. So 2 are coming from here, and 2, I need to generate some versions of these. And this is what I'm doing here. And in order to generate these versions, what I'm doing, I'm considering the Maxwell's equations. Nothing new. Maxwell's equation. What is this? Which law is this one? Does anybody remember or forgot? Yes, Ahmad
Conservative of electric field.
Ahmad Al-Ghazwi, can you tell me what is this law? Ahmad, sorry? I couldn't hear you. Can you tell me again?
It's Laplace equation.
No, it's not the Laplace equation. It is not del square. So what is this? Forget, see, this is coming from, our assumptions that we are applying in regions where there are no charges or currents. So this is actually coming from where?
Gauss's law, maybe.
Gauss's law. Right?
Yes, that's
Yes.
right.
And what is this one? It's coming from?
Faraday.
Modified Ampere's law. See, this is Ampere's law. Modified. See, this is modified by Gauss.
But doctor, shouldn't be there a dot between
Yeah, this
the
is
del
what
and
I'm
the.
thinking. I think there is a small mistake in my notes. Let me check. Is it really a Gauss's law? Just a second. There should be a dot here. 1 minute. Yes.
Should be divergence.
Divergence of E is equal to 0. No, just a second. Oh. Yes, there should be a dot there. Yes, there should be a dot there because this is coming from Gauss's law, which is rho v. So we don't have any charges here. So that's why it is. So this. Here also we don't have any current here. So that's why we are getting del cross H bar as epsilon dou E bar over dou T. Okay, so I will correct this. So it should be a dot here. Now let's continue. So excuse me. So del dot E bar is equal to 0. So now if I may open this del dot E bar, I'm now, if you see here guys, what I'm doing, I'm writing 2 tangential components and 1 normal component, which is typically the case, right? Because for any electric field, if this is my plane, for any electric field, if this is my plane, then there will always be 2 components which will be tangential and 1 component which will be normal, right? 2 components which will be tangential and 1 component which will be normal. So that's why I'm now writing here as 2 tangential components and I'm naming it as I and J, and 1 normal component, which is N. So you can assume that if this is my X, this is my Y, and this is my Z, then this will be X, this will be Y, and this will be Z. So it will be dou EX over dou X plus dou EY over dou Y plus dou EZ over dou Z. But I'm not using this X, Y, Z. I'm just getting a generalized boundary condition. So therefore, if this is equal to 0, Now from in here, let's substitute our previous boundary condition. The previous boundary condition says that the tangential components are 0. So if these two components are 0, that means this is 0, this is 0. Then what I'm getting? I'm getting this as 0. See, this as 0. So this will be my third boundary condition. Now here also I'm doing the same. I'm now opening this del cross H and I'm writing it here. And then I'm opening this E bar and I'm writing it here. So E bar has two tangential component and one normal component. My magnetic field also have two tangential components. See, HTI and HTJ and one normal component. And I open it here. So once I open it, then I substitute all the boundary conditions, all the values that I got from the boundary conditions. So what are those? The normal component of magnetic field is 0. So this is 0. The normal component is 0. Then here, what do you know? The tangential components are 0. So the tangential components are 0. And then remove all those terms which are already 0. This one, this one, this one, and this one. And then write it down. This is your expression. And from this expression, if you see here, we have only on the right hand side, we have the normal component. But on the left hand side, we have both tangential component and the normal component. So if we equate them, what does that mean? That means this and this must be equal to 0. That means this and this must be equal to 0. And what are these? These are nothing but both are the two tangential components. And therefore, I can generalize that the tangential component of the magnetic field, dou HT over dou N, is 0. The tangential component, when you find its derivative with respect to your normal space variable, is equal to 0. That's it. So we will stop here, guys. So we got our 4 boundary conditions. These are the 2 typical ones. These are the 2 that we got. And now we will go ahead and we will solve it in our next class. Okay. So we will stop. Thank you very much.